my screen so y'all can join me. Alright, so this first question tells us that there's going to be an SN1. We really don't need that information. We should be able to predict an SN1 here, mainly because we don't have a strong nucleophile. So signs of an SN1 are, first of all, that the leaving group is attached to a tertiary carbon. So it's too crowded for an SN2 to occur. And also we have a weak nucleophile. So it's not likely to come in and push out the leaving group. Plus what we also notice is the leaving group is not a very good leaving group. If it were to leave now, that would produce a negative charge on that oxygen. So that's not likely to happen. Producing a negative charge on the oxygen and a positive charge on the carbon at the same time would be pretty unstable from a stable neutral molecule. So that would require a large activation energy and would almost never happen. So that's why the acid is here. The H2SO4 and the methanol, which is your solvent. Methanol is similar to water, except we have a CH3 group here instead of a hydrogen. But we have a large partial negative on that oxygen, just like water. And sulfuric acid has one of the lowest pKa values, which means it's one of our strongest acids. So normally we think of these as being double bonds. And the reason why it's such a strong acid is because if this picks up a proton, the electrons would remain behind, and the negative charge here would be stabilized through resonance. So the sulfuric acid methanol combination is going to react through a proton transfer to create the very stable conjugate base of sulfuric acid and the conjugate acid of methanol. I could look at the pKa of this, which is going to be around -1, -2. The pKa of sulfuric acid is more like -10 or 11. So this equilibrium definitely favors the side, like any acid-base equilibrium, with a higher pKa value. So this would have already occurred before this other molecule even probably gets involved. But once I create this, this is now a strong acid. It has a negative pKa value. So when that molecule comes in contact with the molecule in the question, there's going to be a proton transfer here. And so that will make this OH into a much better leaving group. So we can do the SN1 process that's happening here. So making a water leaving group. So this equilibrium, which also produces a methanol, when the conjugate acid of methanol donates a proton, if this oxygen here is protonated or if this one here is protonated, their pKa values are pretty similar. So this is going to be a real equilibrium where that proton will be shuttled back and forth. It would be on this oxygen in some of the molecules. It would remain on this oxygen in some of the molecules. But as long as a few of the molecules form this, now they're quite unstable at the formal positive charge. So now that leaving group is much more likely to leave. And that produces the tertiary carbocations. And you see a carbocation also producing water. Anytime I see a carbocation, I want to consider the possibility that it might rearrange. Not likely to happen here though, because it's already tertiary. And the only thing more stable than a tertiary carbocation would be one stabilized by resonance. But there's no way to move this carbocation into an allylic or benzylic position, so we're not going to have resonance stabilizing it. So that would be there. If the methanol is our solvent, it's much more likely that a methanol would collide here than for the water to come back in, but the water could come back in, so this could be reversible. But if the methanol comes in, and it would do that most of the time because of it'd be the solvent, it'd be just a more likely collision to occur, then I would get the methanol, the result of the methanol attacking. So this is a nucleophilic attack on a carbocation. And then this is still positive, so another methanol molecule would pick up that proton, and that last proton transfer would produce a product, and it would reform this initial molecule, which could then go forward and start another reaction with another one of the initial reactants. So that kind of regenerates the acid catalyst that helps to facilitate this mechanism. Any questions about that? So the other question that was asked about Chapter 7, so we can review what we talked about last week, which we're going to have exams on this week, starting tonight. This question, 7.23 from the textbook, we're treating this structure with H3O+, and we're told it affords or produces a compound with no chiral centers. So right now, I've got two chiral centers. They're both happen to be R. So just treating this with H3O+ will produce a molecule with no chiral centers. So we're going to try to imagine what that mechanism would look like to try to explain that outcome. So it'll be similar to the last one. If I have a poor leaving group, I don't expect it to be able to leave, especially if a molecule is relatively stable and neutral. If we were to imagine how the free energy would change, and this molecule is quite stable, pretty low in free energy. If the leaving group were to just leave, that would create an OH- and a carbocation, and those would be much less stable in comparison, so this would be a very large activation energy to produce a pretty unstable set of intermediates. So very few of the collisions this molecule will undergo will have the energy necessary to do that and just have the leaving group leave, as we said in the last example. So that's why the H3O+ is here. The H3O+ is going to get this process started by being unstable. So since I've added an unstable reactant, I don't only have these stable molecules, I've got other reactants that are unstable. So my reactants on average are relatively high energy due to this unstable high energy formal positive charge on an oxygen. So this oxygen here could pick up this proton. These electrons would stay here. And that would give me a water leaving group here. And that would be in equilibrium, because as we said, positive formal charge on an oxygen. It's not stabilized by resonance or induction or any other factors in stereo. So both of those are similar in stability, and the equilibrium could readily favor kind of both of them at the same time, be pretty balanced equilibrium. But now that my molecule is unstable as an intermediate, it would be more stable than if I had both a negative and a positive form, because there's only one formal charge there, and when the water gives up a proton, it becomes neutral. So this intermediate may be only slightly higher than the initial compound, which means most of the collisions might have the energy to transfer that proton. Then the next step would be the loss of the leaving group. So now that it's relatively unstable, it can undergo a minor collision, which would go up here and produce the carbocation. So the loss of the leaving group there produces a secondary carbocation. As we said in the last example, every carbocation you see, you should at least consider the possibility of a rearrangement. So this carbocation is secondary, and I see, okay, there's a hydrogen here, and if that hydrogen were to shift over to do a carbocation rearrangement, then I would produce a carbocation here. So in terms of the chiral centers, which is what this question is really focused on, I lose one chiral center when the leaving group leaves. It's no longer a chiral center. I lose the other chiral center when the hydride shifts over, because now I have no chiral centers in my structure, right? So this molecule here is not a chiral center. First of all, because it only has 3 things attached, so it can't have 4 unique things attached, but also because these 2 ethyl groups are now identical attached to it after the rearrangement. So then a water, which would be the only possible nucleophile around, could come in there and attack, and that would produce. So now that this is flat, and the p orbital is sticking out both above and below the plane, the water can attack from either the top or the bottom. So if I imagine it attacking from the top, I get this structure. If I imagine the water coming in from the bottom, it would end up pointing away from me, the dashed wedge. And that would force the methyl group out toward me. And what's the relationship between these 2 structures? They're the same. I'm not producing a chiral center because this ethyl group and this ethyl group on that carbon are the same. So if I flip it over like a pancake, this ethyl group will lie right on top where the other one is, but the OH2 plus group would end up flipping over underneath the molecule and look like this, and the methyl group would end up flipping on top of the molecule and look like this. So these 2 structures are just pancake versions of one another. So I don't need to draw both of them. They're the same structure. And then the last step, a proton transfer would occur to balance the charge here, so another water molecule would regenerate H3O plus by picking up this proton. These electrons would stay behind, and I would produce this alcohol. So I don't really have to show a solid wedge or a dashed wedge because there's no difference in the identity of the structure either way. So with no chiral center here, I don't have a chiral molecule anymore. Any questions about that one? Alright, so that's some good mechanism work related to the stuff that you might deal with tonight. So there's a lot of details involved in that. Hopefully you had a chance to look at a lot of practice over the weekend and check your work, and you're in good shape. If you don't feel confident for the exam this week, you should probably try to set up a time to discuss some of these and look at some of the details with me. Next week's exam is going to cover Chapter 8. So I want to get into Chapter 8 here, talk about some of the necessary concepts there. So in Chapter 7 we talked about substitution reactions. Here in Chapter 8 we're going to talk about elimination reactions. And while the products of these 2 reactions are quite different, some of the mechanism steps are very similar, and the ingredients involved are quite similar. So we're going to see both mechanisms involve the loss of a leaving group. The difference between substitution and elimination is, in a substitution, I have a molecule that acts like a nucleophile and comes in and replaces the leaving group. Whereas in elimination, I have another molecule that acts as a base. And instead of coming in with a lone pair and attaching to the carbon where the leaving group left, it's going to attach to the beta proton. Right? If it's a base, by the Bronsted-Lowry definition, it's picking up a proton. So we're picking up the beta proton. Why? Well, maybe because the carbon the leaving group's attached to is too sterically hindered, so it can't make it in. Or maybe the structure of the compound just makes it more likely to pick up a proton and share electrons with a hydrogen than it is to share electrons with the carbon, which is what a nucleophile typically does. So a base and a nucleophile are very similar. A base has a lone pair, A nucleophile has a lone pair. The difference is the base picks up a proton, whereas the nucleophile attacks typically a carbon to push out a leaving group. So we're going to look at some detail about what structurally makes a molecule more likely to pick up a proton versus what structurally makes it more likely to start sharing electrons with the carbon. So we can talk about the differences between these reactions and try to predict, if you're given a set of reagents, whether or not one of your reagents is more likely to act as a base and perform an elimination reaction, or whether it's more likely to act as a nucleophile and do a substitution reaction. So here are the structural outcomes of those two reactions. So as we said, in a substitution reaction, we expect the substance to come directly into the carbon where the leaving group's attached. That's called the alpha carbon. And when the leaving group leaves, the nucleophile is there replacing it. And as we saw last week, that could occur by SN2, like I've shown here. Or the leaving group could leave first and create a carbocation, and then it could come in, and that would be an SN1. Alternatively, in an elimination reaction, the molecule that needs to start sharing electrons to balance its charge, instead of sharing them with the alpha carbon, it could share them with the beta proton. So this is the alpha carbon here, this is the beta carbon here, and a hydrogen or proton bonded to that beta carbon is a beta proton. So if the oxygen picks up a proton, then these electrons can move in here and push out the leaving group. And that's an elimination reaction. So it depends in part kind of on randomness, like where is this going to collide? Is it going to be drawn into the carbon? Is it going to be drawn to this, more likely to collide at the beta proton? So we're going to talk about factors that affect that and how to predict what's going to happen there. And sterics is definitely a big issue. We're going to see in detail how if this center is too sterically hindered, it's just not likely to collide there. But the hydrogens almost never sterically hindered because they don't have multiple bonds with multiple electron clouds. They just have one electron cloud. And so usually a base, anything that's strong enough to start sharing its electrons with the carbon is often strong enough to start sharing electrons with the hydrogen, and the hydrogens are often more available. So we'll see how sterics plays a role there. But since we're forming a double bond here, right? So as these electrons swing in, they become a pi bond as the leaving group leaves. So we had one hydrogen there and two here. So these are remaining. So what we're eliminating is one hydrogen and the leaving group. And we're replacing them with the electrons that were shared with the hydrogen. It's always those electrons that become the pi bond. So we're forming a hydrocarbon that's no longer saturated with hydrogens. So it's not an alkane, it's an alkene. Anytime I've got a double bond in my parent chain, it's called an alkene. And so before we get into the reaction here in detail, I want to just talk a little bit about alkenes in general. So I'm going to skip through these slides. You can just look at them. There's a lot of interesting structures that produce a variety of properties for natural products. A lot of them have biological or medicinal relevance. A lot of these happen to be pheromones with long nonpolar chains. Where do we get alkenes? Well, we pretty much get them like all other carbon compounds from petroleum or crude oil. So when petroleum is mined or extracted from the ground, and it is a limited resource, and we need it to produce all these important molecules with all these interesting properties that are valuable to us, it's much more important to try to conserve it so that we can continue to make these interesting compounds that have value than to just burn it up. But when ethylene and propylene are collected from petroleum, there's a variety of reactions that they undergo to produce interesting compounds that have a variety of properties. So they can be connected together in a long chain, and that makes your grocery bags. Polyethylene, polypropylene, very similar properties. Polyvinyl chloride piping is very common in the word is not coming to me. That's weird. Anyway, polyvinyl chloride is used in pipes a lot, and these other compounds are often used as solvents or as precursors, like we showed last time. The ring strain here, you can make this molecule from ethylene, and then you can open it up and produce ethylene glycol and a variety of other compounds. So these are used as precursors, and then reactions are used to build up their structures into a variety of different interesting molecules that have a variety of different uses in society. So that's just a little bit of informational stuff there. So when it comes to an alkene, we also want to make sure that we can name them, just like we learned how to name alkanes. The difference is the ene suffix instead of the ane suffix is used to indicate that there's a carbon-carbon double bond in the chain. A couple other modifications to the naming system. We want to give the carbon-carbon double bond the lowest number possible, and that's going to take priority over other substituents. So that's going to take a priority over alkyl groups and halide groups. So if I have a chlorine, bromine, or iodine, or if I have a methyl, ethyl, propyl, etc., I'm not so worried anymore about giving them the lowest numbers on the chain. My priority is to give the double bond that's part of the parent chain the lowest number possible. And then we're going to modify the suffix. Instead of using like methane or propane, we're using ene as the suffix instead of ane as the suffix. So let's look at some examples on how to do that. So if I have a double bond here, I still have 5 total carbons in my parent, so it's still pent. And if I have a double bond there, I change the suffix to ene, so it's pentene instead of pentane. I do have to make sure that the double bond is included in my parent chain. There are exceptions to that, but we're going to probably exclusively look at molecules where you can actually put the double bond into the parent chain. So do that pretty much every time. So that means even though I can find 8 carbon chain here, I don't want that to be my parent chain. Instead, I'll go with the 7 carbon chain that includes the double bond and make that my parent chain. So no longer is the longest chain of carbons necessarily the parent. Now we want to look for the longest chain of carbons that actually includes the double bond in that chain. And as we said before, we want to give the double bond the lowest number possible, and when we're giving it a number, you'll notice that the double bond bridges 2 carbons. So if I were numbering this parent chain, it's got 7 carbons. I could number from left to right, or I could number from right to left. If I number from left to right, what number do I give the double bond? Well, it's bridging carbon 2 and 3. So how do I communicate about that? They just decided when they designed the system to use the lower of the 2 numbers that double bond is bridging. So it's the 2 that is the locant, or tells us that the double bond starts on carbon 2 and continues to carbon 3. But they only put the 2 in there telling you which carbon the double bond starts on. So that's my concern. I don't want to number from the right to left, because then I don't get to the double bond till carbon 5. And my concern here is to give the double bond the lowest number possible, not really worrying about where the other substituents end up. They'll end up wherever they end up, and in this case they'll end up on 5, 5, and 6. So that would be 5, 5, 6, trimethyl, 3 methyl groups, and then I would have a 2 to indicate where the double bond is, peptene. right? So when I see the ene suffix, I know to look before to see what carbon of the parent chain that double bond is starting on, and then I presume that it's going to be connecting carbon 2 and 3, or the next carbon, right? If the double bond were over here, then it would be 1 heptene, because it would be bridging 1 and 2. When you give the location of the double bond, there's actually 2 different ways you can do it that are both perfectly correct and both acceptable. And that is to put the number 2, since the double bond starts on carbon 2, right before the entire parent name, or you can insert it right before the suffix. Either way is fine with me. So that's totally fine either way. Alright, so here's an example. I want to name the structure. So normally I might look at the ring as my parent, but since the ring does not include the double bond, I want the parent chain to include the double bond. So the longest chain I can make that includes the double bond is 5, right? Once I get to 4, any one of these carbons could be carbon 5. So my parent here is going to be pent for 5, ene, because I've got a double bond, so I can put the 2 here, or I can put it in front. So 2-pentene and pent-2-ene are the same. And so that's just the name of my parent. Then I have to obviously name the substituents. So I've got the substituent here on carbon 2. So it's a cyclohexane. It's not cyclohexane because it's not my parent chain. Only the parent chain will have the ane or ene, or when we start talking about triple bonds, yne suffix. But it's a substituent, so it takes a YL suffix. So I've got 2-cyclohexyl as my one substituent that's on carbon 2, and then I've got 2 methyl groups that are both connected to carbon 4. So I need a number for both, and the prefix to indicate that there are 2 of them, 4,4-dimethyl. And then in terms of alphabetizing, if I recall correctly, the cyclo prefix does count alphabetically, but the di prefix does not. So I'm comparing the C of cyclo with the M of methyl, and obviously C comes before M alphabetically. So 2-cyclohexyl, 4,4-dimethyl, and then I could choose either one of those 2. I'll just go with the pent-2-ene. Then I want to look always for chiral centers, because if there's a chiral center somewhere, which there isn't in this structure, I would need an R or an S configuration in parentheses out front. This particular double bond does have an E or Z configuration, but we'll worry about analyzing that when we talk about that a little bit later in the lecture today. So I would need to put out front here E or Z. I'd have to make that determination, and that should be part of the name. But we'll talk about that in a few minutes. So that part of the naming system we will discuss here very shortly. Actually, let's do that and come back. And then we can we'll use that as another example to illustrate that concept. So previously we have talked about cis versus trans. We said when I have a double bond, because the p orbitals have to overlap side by side, that double bond cannot rotate. When it's all shown with regular lines, it's in the plane. If I tried to bring this in front by lifting it up and like rotating it out, well then the p orbital here would no longer be in the same plane as this one. They wouldn't overlap. And I have to put in energy to break the pi bond to do that. So typically at room temperature, there's not enough energy to rotate. So that's why we said before that chemically this structure and this structure are different. There's no way to rotate the pi bond at room temperature to get them to be superimposable. So they're not superimposable, but they still have the same name otherwise, so that makes them stereoisomers. They're not mirror images though. So what type of stereoisomers are they? They're diastereomers. Diastereomers because they're non-superimposable, non-mirror images, but the atoms are all connected the same. The only difference is the spatial positioning of this methyl group, whether it's spatially positioned this way or spatially positioned up in that direction. So what we said about cis was, anytime I have a double bond, if two identical groups are on the same side, that's cis. If I have two identical groups on opposite sides, that's trans. So we'll see a variety of examples where that's true, and then we'll talk about how to include that in the naming system. Typically, if I have a double bond in a ring, only the cis is stable, right? So here, the two hydrogens are on the same side of the double bond, two identical groups on the same side of the double bond in each one of these. As long as my ring has fewer than 8 carbons in it, I can't make a trans double bond, right? If I tried to do that with like a 6-membered ring, I'd have to have something like this. Right, so 1, 2, 3, 4, 5, 6. So 6 carbons here, and I'd have a trans double bond. Well, that would create a huge amount of angle strain, because this ring, in order to reach all the way around there and keep the correct angles, 120-degree angles on these sp2 hybridized carbons, the other angles would be warped, and it would create a lot of angle strain and repulsion between electron groups on the same carbon. So that is prohibitively unstable. Once I get to 8 carbons, though, I can create a trans double bond. So if I have 8 carbons in a ring, maybe 1, 2, 3, 4, 5, 6, 7, 9, 10. That's 10. 8. Let's try this a little differently. One, 2, 3, 4, 5, 6, 7, 8. So once I get to 8 carbons, then I can make a trans double bond. I've got enough carbons where even with the 120-degree bond angles here, there's enough carbons to keep the sp3 hybridized carbons at roughly the correct angles. It doesn't create too much angle strain, and I've got enough carbons to reach all the way around there. So if the ring is big enough, you can make a trans double bond where the hydrogens are on opposite sides within the ring, but if the ring is too small, you can't do that. And that also applies to bicyclic alkenes. So for example, here in red here, I've got a 6-membered ring. And so part of the problem here is I've got this black bonds shown here that would be blocking where the p orbital would normally be, right? When I normally have a pi bond, it's normally because the p orbitals are perpendicular to the plane of the atom. So here I would need a p orbital here and here to create that pi bond, but this p orbital would be basically right where that sigma bond would be, and that would not be possible to have 2 orbitals in the same spot. So this p orbital here wouldn't effectively overlap with the other one due to all of the other sigma bonds in the way. So that's not going to be a stable pi bond. So we can think about that situation. Here though, once I extend my ring to 8 carbons or more, now I can actually find a little bit of space to put that orbital in there and do the proper overlap, and so that compound isn't nearly as stable. So the angle string created by a small ring that has a trans double bond is too unstable. And in addition, if I tried to do a bicyclic system, the p orbital and the sigma bond overlapping creates too much repulsion. So that one's not stable versus if I have 8 or more carbons. That is possible to connect a double bond to the bridgehead. So Brent's rule basically says you can't connect a double bond to the bridgehead carbon unless you have 8 or more carbons in the ring. So that's a minor topic. I probably won't ask you about that specifically. So we know that we can't really rotate this pi bond. At room temperature because there's not enough energy to break it. And so is this one cis or trans? Well, we said we need identical groups. So right now I've got an ethyl group and a methyl group. They're not identical. But don't forget, there are hydrogens. So since there's a hydrogen here and they are identical to one another, if I have identical groups on opposite sides of the double bond, that makes it trans. So this is, you could call this trans 2-pentene. And that would be enough information to show that it's different from the cis 2-pentene. So as long as there are two identical groups, and I can show that they're on opposite sides or the same sides, the trans versus cis nomenclature is adequate in the name. But there are some molecules that don't have any identical groups. So if we look at this example down here, I've got an ethyl, I've got a hydrogen, a fluorine, and an NH2. So none of these are identical. So I can't really label this as cis or trans. I can't give it a cis label, I can't give it a trans label, and the same for the structure over here. But these two structures are not identical. The relationship that they have is that they are via stereoisomerism. They're not identical, so they do need to have different names. So because the cis-trans nomenclature doesn't apply, if I were to name these structures, I need a different way to differentiate between which stereoisomer I'm dealing with. And so that's where this EZ notation comes in. So we're going to talk about that here in the next few slides, and we can go back and apply it to those examples, including the quiz questions. So the way you determine whether a double bond has an E or a Z configuration is to prioritize the two groups that are on one carbon based on their atomic numbers, the same way we would prioritize groups to determine an R or S configuration on a chiral center. But this center only has 2 atoms attached. Obviously it's double bonded to here, but we're only looking at the 2 groups attached to this carbon that are not part of the double bond. So fluorine has a higher atomic number than carbon. So priority 1, priority 2. So I'm prioritizing the 2 groups on this carbon, and then separately I'm prioritizing the groups on this carbon. So sometimes students get confused and try to prioritize groups on different carbons. Don't do that. You only need to prioritize the 2 groups on the same carbon. So over here, obviously nitrogen has a higher atomic number than hydrogen. So I'm going to prioritize the groups. And then if the 2 priority groups, so even though they're not identical, and I can't call this cis because I don't have identical groups on the same side, I do have the 2 top priority groups on the same side, which ends up being Z. If I put the 2 top priority groups, which were the fluorine and the NH2, on opposite sides, that would be E. So where do these letters E and Z come from? Well, they come from these German terms that I'm not even sure exactly how to pronounce for sure, but the word zusammen means together, and the word etgegen means opposite. So since we're not German speakers, it's probably going to be difficult to remember. So you need some way to remember that Z means the 2 priority groups are on the same side, and that E means they're on opposite sides. The way that I remember is I look at the shapes of the letters. So the letter E has 2 things, really 3 things, all on the same side. And the letter Z has 2 things on opposite sides. So for a long time, I used that in my mind, and I began to think that when the priority groups are on opposite sides, that's Z, but that's not true. So personally, I made a big mistake with that for a long time, and I was doing it wrong. And then when I realized I was doing it wrong, that made a big impression on my brain. And so now I just remember it's the opposite of the way I used to do it. So however you remember is fine, but you have to have some way of remembering that when the two top priority groups are on the same side, that's Z, even though the letter Z has the lines pointing on opposite sides of the central line. And when the two top priority groups are on opposite sides of the pi bond, it's E, even though all the lines in the letter E come off of the same side of the central or vertical line in the letter E. So any way you can use to remember that is fine. So let's just practice a couple, and then we'll go back and look at those other structures. So this molecule here, is it cis or trans? Well, what we're looking for are identical groups on adjacent carbons, whether on the same side or opposite side. So clearly it's not cis or trans. I don't have a cis or trans way to label this because I don't have two identical groups on the same side or two identical groups on opposite sides. The only identical groups I have are on the same carbon. And that's not cis or trans. They have to be on different carbons on the same side or on opposite sides to be cis or trans. I also don't have an E or Z here. This molecule doesn't have an E or Z configuration because if I have two identical atoms on the same carbon, how do I find a difference in their priorities? There is no difference. So anytime I have two identical atoms or identical groups here, there's no way to prioritize one over the other. I can prioritize this ethyl group as a higher priority than a methyl because of the extra carbon versus hydrogens. But if the top priority group is on both the same side as the top priority group on the other and on the opposite, I don't have E or Z. I kind of have both, but really I have neither. So there has to be two different groups on this carbon and two different groups on this carbon in order to get an E or Z configuration for my alkene. Alternative, I can also imagine maybe swapping two of these groups. So normally if I take my alkene and I take one of the groups and swap its position with the other group, normally that gives me a diastereomer, but here it doesn't. Right? Because this structure can be just flipped over and it looks exactly like the other structure. There's no difference because these two hydrogens are identical. If I flip it over like a pancake, it's completely superimposable on this structure. So as long as two structures are superimposable, they're never different. They're identical to one another. And so I would only use E or Z in an instance where the molecule actually has a stereoisomer that results from swapping two of the groups. So this one is neither cis nor trans. It's also neither E nor Z. In the second structure here I do have identical groups on the same side and another two identical groups on the same side. So this is definitely cis. And it also has an E or Z configuration, so let's take a look at that. So here, fluorine has a higher atomic number than carbon. Fluorine has a higher atomic number than carbon. So when the two top priority groups are on the same side, that's also Z. So if I were naming this structure, what would its name be? Well, I would have 1, 2, 3, 4 total carbons, so it'd be bute. The double bond starts on carbon 2, so it'd be bute-2-ene. And I could call it cis. Oops. I could call it cis-2-butene, or I could call it trans. Not cis-2-butene, or I could call it Z. I would put that in parentheses either way. So you can name that either way. Oh, Kristen offered a nice way to remember E versus Z. Okay, yeah, feel free to use that method. That makes a lot of sense. It's probably a good way to remember that as well. Everyone's different, so different method might work for you, but you may be asked to analyze that, so you will have to make sure that you have a method that works. So let's check out this structure. Here I'm drawing in my hydrogen to make sure I know what the groups are. So here I do have two identical groups on the same side, so I could call this cis. Oh, by the way, up here, sorry, I also have a fluorine on 2 and 3, so I would have to insert that in the name. It would be 2,3-difluoro. So it'd be cis or Z, 2,3-difluorobutadiene would be an appropriate name for that structure. So down here again, I do have two identical groups, so I can call that cis. Sometimes students get into the idea where cis necessarily means Z, but that's not always true. So once you've determined whether it's cis or trans, you do need to separately analyze whether it is E or Z. And in this particular case, to do that, I'd prioritize a carbon versus a hydrogen, so it would be 1, 2. Prioritize a fluorine versus a carbon, 1, 2. So here my two top priority groups are on opposite sides, which means that one is E. So it's possible for a cis to be Z. It's also possible for a cis to be E. You really need to do both analyses in that situation. If we were naming this structure, we would have 4 carbon chain again, so it'd be bute. And we have our double bond starting on carbon 2, bridging 2 and 3, so buteene. In this case, I would number from this side. That way I give the double bond the lowest value in its locant, and I give the fluorine the lowest value in its locant as well. So the 2-fluoro, I wouldn't need a hyphen there, 2-fluoro-buteene. But then out in front, I either need to put cis or E. On this last example here, I notice that I have two identical groups on opposite sides of the double bond. So when I have identical groups on opposite sides, that's trans. And like cis can be E or Z, trans can also be E or Z. So I need a separate analysis to see here. I've got fluorine as a higher priority than carbon, and I've got carbon as a higher priority than hydrogen, again based on the atomic number. So if the two top priority groups are on the same side, that's going to be Z. So this would be trans or Z, 2-fluoro, 2-butene for the name of that structure. Alright, so let's go back and take a look at these other ones. So is this one E or Z? Well, let's look at the priority. So I've got this carbon here versus this carbon. The first element's the same, so I go to the next element. So the next highest priority element is a carbon attached here and here. Over here, I only have hydrogens. So clearly, this group is a higher priority, and this group is the second priority. On this other carbon of the double bond, I've got hydrogen here, so carbon takes a higher priority than hydrogen. So now I can see the top priority groups are on opposite sides. And when they're on opposite sides, even though there's no cis-trans here, so I can't call this cis or trans, the two top priority groups on opposite sides means that it is E. So I need that in the name. There's no other way to unambiguously communicate about the stereochemical configuration at this double bond, and that the two top priority groups are on opposite sides, giving me the E configuration. I can't use cis or trans in this example. So here were the two molecules that you were to name for today's quiz questions. So this first one is a bicyclic compound. So obviously there's more than one ring fused together here. So I would have a bicyclo, B-I-C-Y-C-L-O, bicyclo. And then I need brackets. And then I want to count the total number of carbons. 1, 2, 3, 4, 5, 6, 7, 8. So oct. And since I do have a double bond in my parent chain, it's going to be octene. But I have to tell what carbon that double bond starts on. So my priority here when I number the parent chain is to give the double bond the lowest number I can. But I have to also remember that when numbering a bicyclic system, I have to start at a bridgehead carbon, which are here and here, and move into the longest loop first and then go to the second longest loop. So in this case, it doesn't matter which bridgehead I start on. I'm going to number into the longest loop, so it's going to be 1, 2, 3. I'm going to get these 2 chlorines on 3, and then I'm going to come around here, 4, 5, 6. I'll get the double bond on carbon 6. If I started here, I'd have 1, 2, 3, 4, 5, 6. So the numbers for the chlorines and the double bond be the same either way. So I'm just going to start here, 1, 2, 3, 4, 5, 6, 7, 8. So that would be how I would number my parent chain. I've got 2 chlorines on 3, so I've got 3, 3, dichloro, bicyclo, oct, and then the double bond is bridging 6 and 7, so I just put the lower of those 2 numbers in there. But then I do need numbers in my bracket because that tells me how the rings are fused. And if you recall, the numbers in the brackets are the number of carbons in each loop, not including the bridgeheads. So this longest loop has 1, 2, 3 carbons in it. The second longest loop has carbons 6 and 7, which are 2 carbons. And the third longest loop has only 1 carbon. So that would be the name of that structure there. Here, it's a bit simpler of a molecule, obviously. So I can find a 1, 2, 3, 4, 5, 6 carbon chain is the longest chain I can make. That includes a double bond. And if I number from over here, all my substituents, especially the double bond, is not going to have a very low number, so I definitely want to number from the side that gives a double bond the lowest number possible. So here I've got my double bond starting on carbon 2, and I've got 6 carbons. So that's hex, ene. So I could do hex 2-ene or 2-hexene, either way. Putting the 2 here still tells me that the double bond starts on carbon 2 of the parent chain. And then I've got a methyl on 3 and a methyl on 4. So I'd have 3, 4, dimethyl, 2-hexene. A lot of people stopped there when I looked at some of the preliminary answers to the quiz questions. But anytime there's a double bond, you have to look for the possibility of it being either E or Z. And if there's a chiral center, you always have to look for the possibility of that being R or S. So let's take a look at those. So let's say I've got my chiral center here. I'm going to recognize that there's a hydrogen coming out at me. That's the 4th priority group. I want to prioritize the other groups. So this carbon here is equivalent to being bonded to 1, 2, 3 carbons. This carbon here is equivalent bonded to 1 carbon and 2 hydrogens. So this is going to be my top priority group. This is going to be my second priority group. This is going to be my third priority group, and the hydrogen will be 4. So if I go from 1 to 2 to 3, and the 4th priority group is pointing out at me, counterclockwise ends up being R. Right? Normally counterclockwise is S, but that's only when the 4th priority group is on a dashed wedge pointing away from you. So I scribbled all over that. So I'm going to redraw it so I can do a good analysis of the E versus Z. So here on the first carbon of my double bond, carbon takes priority over hydrogen, and on the second carbon of my double bond, this grouping of carbons and hydrogens has more carbons. This one has only hydrogens attached, so that would be my top priority, and this would be my second priority. So again, if the top priority groups are on the same side, that ends up being Z. Any questions about those? Alright, so it also turns out that there's a difference in stability between the trans versus cis, and that's based on sterics. So anytime I've got a double bond, prioritizing the groups for an E or Z configuration is different from looking at sterics. Just want to point that out, right? So let's say I have fluorine here on the same side and chlorine here on the same side. So clearly chlorine has a higher atomic number than fluorine. So these two would be on the same side, and that would be a Z or a cis, because identical groups on the same side is cis, top priority groups on the same side is Z. If I compare that to another, the other stereo isomer of that, the diastereomer of that, where the fluorines are on opposite sides and chlorines on their same side, this would be trans or E, because here the top priority groups are on opposite sides. Again, these are diastereomers, but they're not identical. They have different polarities, a lot of different properties, and different stabilities. And the stability when I have a double bond, one thing that affects that is sterics, right? So if in these space-filled models of these two structures demonstrate that. Whenever I have two large groups, sterically large, not necessarily in terms of their priorities with their atomic numbers, but sterics, right? That has to do with the size of the electron cloud. The more carbons and branching I have here, the bigger this electron cloud is going to be. When I have two electron clouds that are both big, you can see they start to get too close together. Right? This cloud is kind of shaped like this, and the other cloud shaped like this. They start to overlap, and that creates repulsion between the clouds. So even methyl groups, which aren't that big sterically, if they get too close together, the repulsion between them will be a problem. It will create instability. It will make the molecule less stable. Versus a situation where those electron clouds are far apart, there really isn't much sterics in this structure. So when it comes to E or Z or cis or trans, we're obviously analyzing the priority of the groups. When it comes to stability, how stable it is, or the potential energy, we're looking for sterics. So in this example here, what's bigger, the cloud around a fluorine or a chlorine? Well, chlorine has an extra layer of electrons. So the chlorine is going to have a larger cloud, and the fluorine is going to have a smaller cloud. So if I put the two atoms with the biggest clouds on the same side, they'll start to repel a little bit. If I put them on opposite sides, they will not be so close, and so they won't cause so much repulsion. So typically, cis is less stable because you have identical groups on the same side, and when the groups are highly sterically hindering, putting those two identical groups on the same side is going to make it less stable. But you really need to look at what the groups are to see how big their electron clouds in order to judge their stabilities. And we can measure that stability difference experimentally. We talked about how heat of combustion can be used to measure the stability of a structure, right? We said if I take a structure and its isomer and react them with oxygen to produce CO2 and water, in both these reactions, I'm converting the reactants into the same set of products, right? This set of products is the same as the other one. And so if one releases slightly more energy than the other, it means it must have started at a higher potential energy to begin with. Right? So how does heat of combustion relate to stability? We could say a higher heat of combustion, which means a greater, actually it'd be better to say more negative value, since heat of combustion is always going to be energy that's released, because CO2 and water are more stable than the hydrocarbon. The higher the heat of combustion, the more energy released, the more unstable it was to begin with, before the reaction. it's starting at a higher potential energy, right? Unstable, higher potential energy, because it has the potential to release more energy. So the difference here isn't a lot, right? These numbers are almost the same, but we can look at the difference graphically here and see the same thing, right? Because of these fairly significant electron clouds causing repulsion, this one's a little bit more unstable. It's a little higher in energy. It's only 4 kilojoules difference, but similar to eclipsing, right? These groups pointing next to one another, their clouds are creating some repulsion. So we already talked about examples where repelling groups like torsional strain on adjacent atoms makes it higher in energy, more unstable due to that extra repulsion. So if it's already higher in energy, more unstable, it has to be more energy going to the same final energy, the same final set of products. So it's the same final energy as the other reaction, but here there isn't as much repulsion, so it's more stable to begin with, and it doesn't release as much energy upon reacting. So make sure you have those concepts straight in your mind, because if I give you heats of combustion for molecules, or ask you to rank heats of combustion for molecules, you'll have to look at the stability of the structures. So I can use heats of combustion to look at stability of other alkenes, and what we see here is a bit of a surprising result. You might normally expect that if I had 1, 2, 3, 4, 5, 6 total carbons, so as long as my molecules have the same numbers of carbons and hydrogens, they're comparable, right? That's what we saw over here. Same number of carbons and hydrogens, same amount of oxygen reacting, same amount of product produced. Whichever released more energy must have started at a higher potential energy or been less stable to begin with. So if we do the same experiments, we're not working with numbers here, we're just working with a ranking. You might expect that these methyl groups here would cause some repulsion and that this will be less stable. And that is true. But there's something else at play, because if you actually measure the heats of combustion for these, you see that this one actually releases less energy, or its delta H of combustion, the negative value, is a smaller negative value versus the one over here that has a larger negative value. And so you can analyze the heat of combustion for a variety of different compounds, and what you'll see is a pattern or a trend. And I don't really have a good explanation for this trend, so you don't have to worry about explaining it. But you do have to remember that when I have a carbon-carbon double bond, it's going to be more stable in general if there are carbon groups directly connected to the atoms that have the pi bond, versus if it's mostly hydrogens. So the book says one way to think about this is the more substituted your pi bond is with carbon groups, the more stable it will be, versus if the carbon-carbon double bond is substituted with hydrogens, or isn't substituted with carbons. So they just say substituted. If it's more substituted with carbon groups, less substituted with carbon groups, the more substituted it is, tetra meaning 4 versus mono meaning 1. Tri is more substituted than di. All right, more carbon groups substituted on that double bond, the more stable it is, and so it will release less energy upon combustion. So I might give you a question like this to test your ability to make that analysis. So if I give you 3 names, and you're trying to order their heat of combustion, which relates to their stability, first thing you want to do is obviously draw their structures. Right? So we use a name to draw the structures here. Here I've got pentadiene. Right? Di is a prefix meaning 2. So this means I've got 2 double bonds, and that's why there are 2 numbers here. So I've got 5 carbons in my parent chain. I've got 2 double bonds, one starting on carbon 1 and one starting on carbon 3. So if I number this 1, 2, 3, 4, 5. One of my double bonds bridges carbon 1 and 2. That takes care of that number. And the 3 means I've got another double bond bridging 3 and 4. And then I've got 3 methyl groups. Trimethyl, right? So I've got a methyl on 2, 3, and 4. So 2, 3, and 4. So that's that structure. This structure here I want to take a look at so I can compare their stabilities. So here I've got a 1,4 pentadiene. So I still have 5 carbons in my parent chain. But here the first double bond starts on carbon 1. And the second double bond starts on carbon 4. 1, 2, 3, 4. And on carbon 2 I have an isopropyl. The next structure I've got hexadiene. So now I've got 6 carbons in my parent chain. I still have 2 double bonds, that's why it's a diene. 1 double bond starts on carbon 1, 1 starts on carbon 5. And then I've got methyls on 3. 1, 2, 3. And then finally, here I've got cyclohexene. There's no number here telling me where the double bond starts. There's no number between the hex and the ene. There's no number in front of the parent name. So that means that the double bond starts on carbon 1. If there's no number shown, you assume that it's going to be on carbon 1. So if I just number this carbon 1 and this carbon 2, my double bond would have to be there. So then I've got 3, 4, 5, 6 for my cyclohexene. And I've got methyls on 4 and 5. So when it comes to judging the stability and heats of combustion, so let's call this A, B, C, D, so we can rank them. So I'm going to go from least stable to most stable. And the least stable is going to have the highest heat of combustion because it has the most potential energy to release upon being converted to CO2 and water, and so this would have the lowest heat of combustion. So what are the factors I want to look at here? The first factor, the most important thing here, is the fact that sigma bonds are more stable than pi bonds. Right? We've talked about that earlier in the semester. We said sigma bonds involve the electrons held for the most part between the nuclei, attracting effectively to both. But pi bonds involve a node in the plane of the nuclei and the electron clouds above and below that plane, so the electron density can't attract and get as close to the nuclei. So we know sigma bonds are more stable. So if I count up all the sigma bonds and pi bonds in the structure, I'll find that D has 1 sigma bond more than C, B, and A. A, B, and C all have 1 additional pi bond, right? I can see it. I've got 2 double bonds here, 2 double bonds, 2 double bonds. Here I only have 1 double bond. The rest of the bonds are all sigma bonds. So with the extra sigma bond, I know D is the most stable with the lowest heat of combustion. So if I can see one of my molecules has more pi bonds and the other has more sigma bonds, the one with more sigma bonds should be more stable and have a lower heat of combustion. So then the next thing I want to look at is the degree of substitution at the pi bonds. And we just saw that one on the last slide where I want to count if I have a pi bond. What we said was if there's a carbon group there, it's more stable. If there's a hydrogen, it's less stable. So I'm going to look at each pi bond in each of these structures and count for the pi bond how many positions are substituted with carbons versus how many positions are substituted with hydrogen. The more carbon substitution there is, the more stable the pi bond will be. So in molecule A, I've got 1, 2 hydrogens and 1 carbon group here on this on the carbon 2 of this pi bond, and another carbon group on carbon 2 of that pi bond. The other pi bond is only substituted with carbon groups. So 1, 2, 3, 4 carbon groups on that one. So I've got 6 carbons and 2 hydrogens if I count up all the different groups that are substituted on each of the pi bonds. I want to analyze each pi bond separately and count all that up. Over here, this pi bond, I've got hydrogen, hydrogen, carbon, carbon. And this one, I've got hydrogen, 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 carbon. So here I've got this carbon's got 2 carbons attached to it, this carbon's got 1, so only 3 carbons and 5, no, 1, 2, 3, 4, 5, right, 5 hydrogens. And then the last structure here, these pi bonds are almost exclusively substituted with hydrogens. 6 hydrogens, this carbon is bonded to a carbon, and this carbon is bonded to a carbon, so 2 carbons and 6 hydrogens. Not worried about D because I already established D is more stable based on factor 1. So I'm looking for more carbons directly bonded to the carbons involved in the pi bond. That's going to make it more stable. So I can say A looks like it's more stable than B and C. B looks like it's more stable than C because there's more carbons substituted on the pi bonds compared to C. And C has the least stability because there's only 2 carbons substituted on those pi bonds and more hydrogen substituted on them instead. Alright, so that gives us the ability now to judge the stability of alkenes and to name them and to describe them. And so now we want to look at some reactions. And we definitely wanted to talk about this first because we need to be able to recognize that if a molecule has the possibility of producing an alkene in one or another position, we need to be able to judge which position the alkene might be more stable in, and that can help us to more correctly predict the outcomes of some of these elimination reactions. So as we said, elimination overall involves getting rid of a beta proton and the leaving group on an alpha carbon. So we're going to get rid of those, and we're going to replace these 2 sigma bonds with a new pi bond. And also, there will always be a base picking up that hydrogen, so this won't be off on its own, it will really be bonded to a base. So we're breaking 2 sigma bonds, we're producing a pi and a sigma. So if I'm breaking 2 sigma bonds, and I have to put energy in to break 2 sigma bonds, that's probably going to take a fair amount of energy to break 2 sigma bonds. And then if I'm only forming 1 sigma bond and 1 pi, the pi bond's not that stable. The sigma bond will release a lot of energy, but the pi bond forming won't release that much energy. So typically, whether this process is 1-step or 2-step, if we're just looking at the thermodynamics and we're just comparing the initial and final energies, we have typically an endothermic process. It's an endothermic process, which means it's going to be disfavored, and we'll talk more about the thermodynamics later. But from an entropy perspective, I have 2 reactants, the base and the other molecule, but I'm forming 3 products. Once the leaving group leaves, the base picks up the proton, and I have an alkene. 3 separate things are going to be able to bounce around with much more variety and randomness in their positioning and motion. So going from a low entropy to a higher entropy with more moles, that's the saving grace for these reactions. The fact that there's an increase in entropy means that is going to be favored thermodynamically. And so when we look at whether or not these processes overall will be reactant or product favored, since delta S is positive, this negative sign here means this is the term. We need to make this term large enough, largely negative enough, that it will be enough to overcome the fact that delta H is positive in most of these reactions if we want to get a negative delta G and actually make the reaction product favored. So that's a little bit of a head start on the thermodynamic analysis there. But when we're talking about the mechanism, we're more interested in kinetics, right? We want to also understand how can we control where the collisions occur and get the products that we want to get. And that involves detailed analysis of the collisions and the movement of the electrons in the mechanism. So we're going to be looking again at the same type of electron movement we looked at in Chapter 7 and analyzing that from a kinetic perspective. So just to quickly review, what are the 4 steps we talked about? Well, there's nucleophilic attack, loss of a leaving group, proton transfer, rearrangement. So which of these absolutely must be present in any elimination mechanism? Well, nucleophilic attack is definitely present in any substitution mechanism, but not typically in an elimination mechanism. So if we're going to do the elimination, what's happening here? Well, we have a leaving group and we have a hydrogen. Right? The leaving group has to leave, so that one is definitely going to be occurring. And there's got to be a base that picks off this hydrogen. And so there's definitely going to be a proton transfer occurring. And typically these electrons would swing in there to form the pi bond as the leaving group's leaving. So we may or may not see a rearrangement, carbocation rearrangement. Right? So we want to look at that possibility. Right? If the leaving group left first, like if this were a tertiary center, and it could, or maybe they're a resonance, and it could stabilize the carbocation, we might have the leaving group leave first. It might produce a carbocation, and then there could be the possibility of a carbocation rearrangement before the base comes in and picks off the proton. Right, so there's going to be 2 different mechanisms, just like there were SN1 and SN2 in Chapter 7. Here we have E1 and E2. In one of those mechanisms, everything happens at once. In the other mechanism, the leaving group leaves first, and then the base comes in a second step. So the first mechanism that we're going to consider is called the E2. Now this is one step. Why is it called E2? Well, it's the same reason we had SN2. The 2 means it's second order overall. If we have a one-step process, that means both reactants have to collide. And if I increase the molarity of either one of them, I'll increase how often they collide, and that'll increase how often the product's produced. So the rate depends on the rate constant, of course, but also the molarity of the base, as well as the molarity of the substrate, which is this structure here. Right? So if I had more of either one of them, they're going to start colliding more, and the rate of product production will increase. And so since they're both first order, second order overall, that's why it's called an E2. Right? So that's pretty similar to what we said in terms of an E1 or SN2. In the other mechanism, which is an E1, the first step is the exact same first step as in the SN1. So the E1 and SN1 have the same first step. And that's the loss of the leaving group. If the leaving group leaves first, I have a carbocation. Now this is really unstable. So I do run the risk of the base coming in here directly and forming a bond. That would be an SN1. But if the structure is maybe too sterically hindered, or maybe it doesn't form a very stable bond with carbon in general, it might be more likely to pick up a proton, which would push those electrons in it and make the double bond. Or if I increase the temperature, because when the base picks up the proton, it forms a separate product from the alkene. If the base were to come in here and do a substitution, I would form one substance, which wouldn't have that much entropy because all the atoms are connected, and that limits the variety of ways it can move and be positioned. versus when I have two products formed, there's more variety. So increase in the temperature, and this all can be in equilibrium, increasing the temperature can help the equilibrium shift toward the side with more entropy. And we'll talk more about that when we talk about the thermodynamics of these processes. I'm just trying to make sure we keep thermodynamics and kinetics straight. What about the reverse order? Is it possible to do the proton transfer first and then the loss of leaving group? And the answer there is no. If I try to do the proton transfer first, which would be picking off the proton, these electrons would either have to stay on the carbon, which would give it a really unstable negative charge, or I could try to imagine them going in here, but then that would form a 5-bonded carbon, which would be even worse. So the base really cannot pick up the proton unless it happens after the leaving group leaves, or unless it happens as the leaving group's leaving. Right? So if this proton gets picked up and these electrons swing in, it has to happen at the same time the leaving group's leaving. The leaving group can't leave in the second step. It has to happen in the first step. And so if the base is not involved in the first step, and the only thing that's happening in the first step is the loss of the leaving group, that's going to be the slow step, just like it was in an SN1. And the 1 here means that it's first order, right? Because only this reactant would be first order. Right? The rate would be equal to the rate constant times the concentration of this substrate, whatever it is. Since the base would not be involved in that slow step, adding more or less of it would not facilitate collisions in the slow step, and it wouldn't speed up the overall rate. So the base in this case would be 0 order, and the substrate would be first order, and that's how I get first order overall. Alright, so this quiz question about E1 versus E2 mechanisms. Actually, this is a bit out of order here. Let's come back to that one in a couple seconds. I put that in the wrong spot by mistake. Right, so let's look a little bit at the E2 in a little bit of detail here. So we said in the E2, the base picks off the proton, the electrons swing in, push out the leaving group. That all happens in one step, but it's second order overall because both reactants are first order because both are involved in a collision in the only step, which is also the slow step, obviously. So how will the rate change if the base or substrate affect, how will a change in the concentration of base or substrate affect the reaction rate? So it depends on the change, but if I were to double the concentration of either one of these, that would cause the rate to double. Adding more base is going to create twice as many of the key collisions in the slow step. It's going to make the product twice as fast. Doubling the amount of this other reactant is going to double how often effective collisions, doubling how often the product is produced, and so that also makes the rate twice as fast. So since they're both involved in the collision in the slow step, they're both first order, and doubling either one of them would cause a proportional increase in the rate. And that's why it's second order overall, because both reactants are first order in this mechanism. Alright, so let's compare the E2 versus SN2 a little bit. So when we said SN2 cannot occur at a tertiary center, because whatever carbon groups are attached here, if it's a carbon, whatever's attached to that carbon, even if it's just 3 hydrogens, it creates too much of an electron cloud. And whatever the nucleophile is, even if it's very small, 1 or 2 atoms, it's never going to make its way in there. It's always going to be blocked out by the steric hindrance of those 3 carbon groups attached to the alpha carbon. So you can't do an SN2 at a tertiary center. We already talked about that. You can do an E2 at a tertiary center, though, because in an E2 mechanism, the base does not have to make its way all the way in to the alpha carbon. It also doesn't have to make its way into the beta carbon. It only has to make its way to the beta hydrogen, which is always right on the surface of the structure, unless it's some crazy structure with some crazy groups that would maybe like reach around here and block out that site. There is a requirement, though, that the hydrogen be anti to the leaving group. Remember, anti, we talked about in the context of Newman projections. We said if a group on one carbon is pointing one direction and the group on the adjacent carbon is pointing 180 degrees dihedral angle from that, that's anti. They're in the same plane, so it's also sometimes called anti-coplanar or anti-periplanar. The textbook uses the term anti-periplanar a lot. That basically just means anti. So this hydrogen has to rotate into the same plane as the leaving group, and they have to be facing 180 degrees from one another. We'll see I think on Thursday why that is. So this hydrogen, once it rotates into the same plane as the leaving group, if the oxygen comes in and starts to form a bond to it, these electrons can swing in there and the leaving group can leave. Just to point out, this requirement is only a requirement for E2. It's not a requirement for E1. But in terms of sterics, it looks good. The oxygen should not have any problem colliding with that hydrogen as long as that hydrogen as long as this carbon-carbon bond can rotate the hydrogen in a position that's anti to the leaving group. So E2 is not really a problem when it comes to sterics. And in fact, if we compare an E2 on a primary carbon versus secondary versus tertiary, we get the opposite reactivity from what we saw in an SN2, right? In an SN2, the nucleophile had to come all the way into the alpha carbon. Well, that can't happen if it's tertiary. And so the tertiary was too slow to even measure. It could happen on a secondary carbon and push out a leaving group, but that was slower than a primary because of the steric hindrance. Well, sterics is not an issue here with the E2, and we can clearly see that experimentally. If we measure the rates, we find even with the extra sterics, the tertiary is more reactive. It's more likely to react than the primary or secondary. And so that suggests if it reacts at a faster rate, somehow that step and the transition state that it goes through is going to be more stable. It proceeds through a more stable transition state. That's the key. If we're talking about rates, we're not necessarily talking about thermodynamics. We're talking about kinetics. We're talking about how often is the base going to collide with a beta proton to push electrons in here and push the leaving group out. And it happens more often on a tertiary carbon than on a secondary or a primary. So we want to understand kinetically why that is. So here's the transition state. Right? If we're interested in kinetics, we're interested in how often collisions occur, how much energy is needed for the collisions, what's happening during the collisions, and that's what the transition state is all about, right? So we said before, the transition state is always the most unstable point during the reaction. It's where bonds are breaking and forming, and when I look at the E2 mechanism, there's a lot of bonds breaking and forming here, right? So just to show the reactants here, this oxygen here, it would pick up this proton, these electrons would swing in here to make the pi bond, and the bromine would leave. So there's one bond forming, this bond's breaking and then reforming over here, and this bond's breaking. Right? So you got a number of bonds breaking and forming. So this one's forming, this one's breaking, this one's forming, and this one's breaking. So each of those pairs of electrons is really pretty unstable in this moment during the collision because they're not in a proper molecular orbital or an atomic orbital. They're in the process or transitioning from one orbital to another, which makes it really quite unstable. So what are the things that can affect how unstable it is, right? If it's a little bit more stable, then the collisions will have the necessary energy more often, and I'll start to make the product more often. So the energy of the transition state can change. It can be made more stable, it can be made less stable, And so what are some of the factors that might affect that? Well, one is the charge, right? When we talked about substitution reactions, we said we need a polar solvent. These partial charges that form during the transition state, if a polar solvent can come in and bring in some partial positive to form attractions, that will stabilize it. It will go down in energy. It will be more stable, so that reaction pathway will happen more often. So we still want to continue to think about the solvent, and in this case recognize that we need a polar solvent to stabilize these charges that form during the transition state. In addition, what we notice here is that this pi bond here is forming. And we already said a few minutes ago that when a pi bond is more substituted with carbons versus when a pi bond is more substituted with hydrogens, there's a stability difference. It's more stable when a pi bond is substituted with carbons. So if my bromine is leaving from a tertiary carbon, which is this carbon here, and there's other carbons attached to it, those carbons also act to stabilize the double bond as it's forming. So a double bond's not just more stable with carbons attached once it forms, it's also more stable with carbons attached as it's forming, in the moment that it's forming. And so if these carbon groups weren't here, and this double bond were forming between two carbons that only had hydrogens, then it would be higher in energy, and it wouldn't happen as often. Right? So that explains this trend here. When the pi bond is going to form between carbons that only have hydrogens attached, it goes through a higher energy transition state, so it just won't form as often. And so here we can see the three next to each other to see the difference. Right, so here is the transition state that's forming between these two carbons. If the pi bond forms as the leaving group's leaving, whatever it is, and there's only hydrogens here, and the base is picking off this particular hydrogen, when that pi bond forms and it's forming between two carbons that only have hydrogens attached, it's not going to be very stable. So most of the collisions aren't going to have the energy necessary to get up there. And it's not going to happen as often. So the rate is slower. In the case of a secondary substrate, that would be in one of these. That means the leaving group's on a secondary carbon. To be on a secondary carbon, I'd have to have another carbon here. That somehow stabilizes the pi bond as it's forming, so the transition state energy isn't high, and a greater percentage of the collisions that occur will be able to get to that transition state and produce the product. And in the case of a tertiary substrate, where both these are carbon groups, that's going to stabilize the pi bond forming even more. So during the transition state, as it's forming, it doesn't have to be as unstable, and so an even greater percentage of the collisions occurring will have that quantity, smaller quantity of energy necessary, and so the product will be produced at a faster rate. Notice the difference between these is not just in the difference of where the transition states are. So kinetically, it's favored to have a tertiary substrate because there's less activation energy necessary, or in other words, the transition state isn't as high in energy, so it'll happen more often. Thermodynamically, we also see a difference in the final energy. And that is because of the product difference in stability. Right? If I'm going to form this double bond, and all I have is hydrogens here on the product that's being formed, it's not going to be very stable. It's higher energy. If the product that formed, at least on one side, there's a couple carbon groups here, that's a more stable pi bond, and so it's going to be a little bit lower in energy than the other ones. So in the case of a more substituted tertiary site where the leaving group's attached, it should make a more kinetically favored process and a more thermodynamically stabilized product. Any questions about any of that? Skipped. What was that? Oh yeah. All right. Alright, so now we have the ability to answer this question. This was, I think it was the last question, the quiz question. So what this question is saying is that the tertiary substrate react faster than primary or secondary. So we just talked about that. We now understand that if the leaving group's attached to a tertiary carbon and there's a beta hydrogen that can rotate into the same plane as the leaving group but be anti, then the base can form this bond. This bond will break and swing in here. This bond will break and come out here. So we'll just do the mechanism. As that pi bond's forming, it's substituted with more carbon groups. So as it's forming, it's fairly well stabilized. So that'll happen more often and through a lower energy transition state than it would happen if there were hydrogens here, if it were primary. Right, so we established that. That's also true for the E1 mechanism, though. Right, so we already know that. If the leaving group's attached to a carbon that's tertiary, it's going to be much easier for it to leave first. So in the E1, the leaving group leaves first, just like in the SN1. So if the leaving group leaves and I get a tertiary carbocation, that's more stable than if the leaving group were attached to a primary carbon. It would almost never be able to leave. It would happen so rarely, it's too slow to even measure experimentally because a primary carbocation that's not stabilized by resonance is extremely unstable. So here we have a situation where the E2 mechanism is favored by a tertiary leaving group, or a leaving group on a tertiary carbon. We just explained that. The E2 favors the tertiary versus the primary. But the E1 also favors the tertiary versus the primary. So if we have a tertiary substrate, how do we know which mechanism it's going to undergo? And the answer is, it depends on the strength of the base. So if the base is especially unstable, then it's just much more likely to collide here and start the process off and push out the leaving group. So if I have an unstable base, it's much more likely to do an E2 because the base is involved in that collision. If I have a more stable base, maybe it doesn't have a negative charge, maybe it's neutral, it doesn't need to share its electrons so much. If it's much more stable, then the base starts at a lower energy. If it's unstable, it starts at a higher energy. So if the base is stable to begin with, in order for it to come in here and collide with the hydrogen and break and form all these bonds at once and get to a pretty high energy transition state, very few of the collisions are going to have the energy necessary to do that. So the stable base lowers the initial energy, makes it unlikely to do an E2 mechanism, because in that case it'd be more likely for the leaving group to just leave first, which would be the lower energy pathway, or the E1. So when I have a stable base, the E1 pathway happens more often. When I have an unstable base, which starts higher in energy, in that case, even if it's tertiary, a carbocation is relatively unstable, so that's not going to be likely to go through a carbocation intermediate if the base is already unstable. Plus, in terms of just the likelihood of the collisions, if this is unstable and it's bouncing around, there's a pretty decent chance it's going to collide with one of these beta protons once in a while to push electrons in here and push out the leaving group. So when I have an unstable base, it's much more likely to undergo the E2 mechanism. So the key difference there is the stability of the base. Alright, so now we want to talk, before we end, a little bit about regioselectivity. So regioselectivity is based on the word region. So we're interested in which region or area of the molecule reacts. When one region of the molecule could react versus another, I get two different constitutional isomers. Right? So here's a question. We've got this structure here. It's got a nice leaving group, the bromine. It could leave. If I want to promote an E2, now that we talked about strong base versus weak base, I would want to make sure that I use a strong base. And we'll talk about what that means in more detail next time, but that definitely at least means that I probably have a negative charge here. And so it's unstable. It needs to share its pair of electrons to balance out its charge. It can't come all the way into the tertiary center because there's too much sterics, so it has to go to one of the beta protons to do an elimination. But in this case I have a beta proton here and I have one here, and they're not equivalent because these two groups are not the same. So if the base picks up this proton and pushes these electrons in here to push out the leaving group, I get this product, which is called the Zaitsev product. If the base comes over here and picks up that proton and pushes these electrons in to form the pi bond on this side, I get the pi bond over there, and the word is cut off. That's the Hofmann product. So there are two different constitutional isomers, right? The difference between these two is not just where the atoms are positioned in space. The double bond is actually connecting different carbons over here than it's connecting over there. So different connectivity gives me constitutional isomers. So these are constitutional isomers. They're very different. They have different properties. They're totally different structures. So I need to think about how can I control this reaction, right? If I want to use this reaction to make a double bond, I don't want to get 50-50 mixture. If I'm only interested in one of these products, I don't want the other one to form. So I want to try to control where the collision will occur. And so that's the next topic that we have to deal with. So these are, real quick, constitutional isomers. And regioselectivity is a question of which region of this molecule, this beta proton or this beta proton, is my base going to collide. And so it turns out you can control where the reaction occurs to an extent if you use bases with different amounts of steric hindrance. Right? So what we're noticing here is there's a methyl group, here's an ethyl group. Methyl group's smaller, ethyl group's larger, right? So the steric hindrance, there's a slight difference here. So if this hydrogen here rotates into a plane that's anti to the bromine, any base can probably get to it. There's not really much sterics going on over here on this side of the molecule. There's nothing really crowding it out. Any one of these bases could come in here and pick up this proton, push electrons in, and push that out. So any of these bases could effectively produce the Hofmann product. And that's what we see. It is produced at least a little bit in each one of these bases, because there's no way to prevent the base from colliding there. There's just no sterics to block any of these bases out, so any of them can collide there. The other position, though, is a little bit more sterically hindered. So if this hydrogen rotates into a plane that's anti to the leaving group, this extra methyl group is kind of blocking things a little bit. So if I do have an especially sterically hindered base, one with this massive electron cloud from these three ethyl groups attached here, if that one were to come in and grab this hydrogen, well, this large electron cloud would start repelling with the electron cloud on the methyl group, and the more steric hindrance there is, the less likely the base is going to collide there. I can also think of it and say that if the base were to collide there, during the transition state or collision, there'd be some steric repulsion between this cloud and this cloud. And when those clouds repel, that would make the transition state energy higher and less likely for the collision to occur with the energy necessary. So that's why with the sterically hindered group here, I don't see the collision occurring at this site. I get very little of this product forming, only 8% of the product forming on that side, because that would require the sterically hindered molecule to come in, and if that side is more sterically hindered, it's just not going to happen very often, and so most of the product's not produced through that pathway. So I can control the regioselectivity with the steric hindrance of the base a little bit. So hopefully you understand now why this highly sterically hindered base gives almost exclusively Hofmann product, because it's so bulky, if it were to come into this side, it would get blocked out, and so that reaction is hindered, whereas the other reaction at the other site where there's not much sterics, it can readily collide there and produce a double bond on the other side of the structure where there's less steric hindrance. So then the question becomes, when I use a smaller base, why am I getting this product over this one? And the answer there is based on the substitution of the carbons involved in the pi bond, right? So we've been saying this multiple times today. If I have a pi bond, it's more substituted with carbons versus a pi bond that's more substituted with hydrogens, the pi bond's more stable when there are carbons attached. That's not just when the pi bond's formed already, but also as the pi bond is forming. As that pi bond forms during the transition state down here, if there are more carbon groups attached, it's going to be more stable as it's forming. And that's what we see here. As this pi bond forms, there's only one hydrogen. It's mostly carbon groups. So this will go through a lower energy transition state, assuming there isn't too much sterics between the crowded groups. And that's why that one's favored forms more often than the other one. So as long as my base is small, and it can access either hydrogen without creating much sterics, most of the collisions will occur at the site that produces a more substituted double bond, because during the collision, as that double bond is forming, it will be a little bit more stable than it would be if it were forming on the other side, where you have hydrogen substituted there instead of carbon. So the Zaitsev product predominates when there is not a sterically hindered base in use, right? So we just said that. The reason for that is because at this site here, if the collision occurs, the pi bond that starts to form in the transition state of the slow step is more stabilized by carbon groups than it would be if it formed on the other side. And so the transition state through which this compound is formed is a lower energy transition state, and so it's formed more often. Also, the product's more stable than the other one, because the carbon-carbon double bond that's formed here is more substituted with carbons than the other one. So both kinetically, it forms more often through a lower energy transition state, and thermodynamically, it's more stable in the end. So if I do reach equilibrium, I should get more of it than the other one. I should be able to produce that product in a reasonably high percentage by using a small enough base that can make it in there and go through the lower energy transition state where the pi bond forms between the more substituted carbons. Alternatively, if I use this bulky base, as we said over here, the sterics that would be created when it comes into the more substituted side would make that transition state higher in energy, so it would happen less often. So even though the product's more stable and favored thermodynamically, it would go through a higher energy transition state when colliding there due to the sterics of this group and the sterics of this group causing repulsion during the transition state, so it wouldn't happen as often. So that's an instance where kinetically I'm getting one product, even though that product is not favored thermodynamically. And so that illustrates really nicely the difference between kinetics and thermodynamics and the importance between the two. So is the Zaitsev product favored kinetically or thermodynamically, or both? The answer is both. The Zaitsev product is more stable than the Hofmann product, and it goes through a lower energy transition state, assuming that the base isn't creating too much steric repulsion there during the collision. So why does the sterically hindered base favor the Hofmann product? That's because the transition state in the Zaitsev product is much higher when there is sterics between the base and the substrate, which is what we just said. So some of the common sterically hindered bases, this one is probably the one the textbook uses the most. Got this nice crowded torbutyl group here, so I can introduce this base into the reaction if I want to make sure it only collides at the least sterically hindered spot to avoid that sterics and the repulsion created by the sterics during the transition state. These two bases are also obviously sterically hindered. They have lots of big carbon groups blocking out a collision that would occur at a highly sterically hindered spot. These are weaker though, obviously without a formal charge. I only have a partial negative here, and so they don't need to pick up a proton as much. So that's why you'll typically see the potassium terbutoxide used most of the time when you're trying to facilitate the production of the Hoffman product. So here the terbutoxide is used. I get mostly Hoffman product. If I want to increase the yield, I could use an even more sterically hindered base, but that might be more expensive. So there might be trade-offs associated with which base makes more practical sense to use. The textbook does mostly focus on this base though, so I'll probably try to use that in most of the examples that you might see with these questions. So then the last discussion point today is this other quiz question. So we're looking for the kinetically favored and thermodynamically favored E2 products. And this is very similar to what we just talked about, right? So when I have a leaving group on an asymmetrical molecule, and that is my alpha carbon, my beta carbons aren't identical. Clearly they have different things bonded to them. I can look at the hydrogen attached here and the hydrogen attached here and try to imagine if I had a base, which side or which collision which collision is going to be thermodynamically favored, which collision is going to be kinetically favored? Well, the answer is it really depends on the sterics of the base. So what conditions can I use to favor each? The sterics of the base is the key factor, which we just saw. So if I use a terbutoxide, and it's a strong base, so it should promote an E2, but it's quite crowded. So for it to come in here and grab this proton with these other carbon groups, not very likely. The sterics probably makes that go through a higher energy transition state than the other side. So with this base, the kinetically favored collision would have to occur on this hydrogen. And just to point out, it would have to be this hydrogen, not this one. This hydrogen is not rotated into the anti-position of the bromine. It's actually gauche. If you remember, gauche is where two groups have a 60-degree dihedral angle. They have to be anti in order to undergo an E2 mechanism. So I'd have to pick off the anti-hydrogen. Its electrons could swing in here since it's in the same plane as the bromine, and that would push the bromine out. In order to have all the electrons flow, the atoms have to be in the same plane. So the kinetically favored product there for a sterically bulky base would produce this double bond here. That would be the product I would create if I form a double bond in the kinetically favored position when I have a bulky base. If my base is smaller, like maybe a methoxide, I probably don't want to go all the way down to a hydroxide, because if it's too small and the leaving group's on a secondary carbon, I might have that come all the way into the secondary alpha carbon and do substitution. So if I'm trying to get elimination, I do want my base to be a little bit bulky so it doesn't come all the way into the alpha carbon and do a substitution reaction. So if this is going to come in here though, I can't really get to this hydrogen. I mean, I can get to it, there's no problem colliding there, but since the hydrogen is gouged to the bromine, the E2 mechanism is not going to work. So in order for this to occur, I would first have to rotate this bond. So if I hold the left side of the molecule still and just redraw it, if the bromine is shown with a solid wedge, the position anti to it is the dash wedge. So I have to rotate this hydrogen, which is currently pointing out at me. I have to rotate this carbon-carbon bond so it's pointing away. And when I do that, that will rotate the methyl group up to here. It will rotate the ethyl group down to here, which you should definitely grab a model, make a model of that to see that if you're not seeing it. That ethyl group would then have a solid wedge, and that would push the hydrogen behind. So now my less sterically hindered base can access this hydrogen because it only has a methyl group. It's not going to create too much steric hindrance with the other groups here, and so it'll go through a lower energy transition state. So this one's also kinetically favored because the base is smaller and because when the electrons swing in here, it's forming a more substituted double bond than I would get on the other side. So that product would form the double bond here. And since this ethyl group and this ethyl group are on the same side during the transition state and it's a one-step process, there's no opportunity for them to flip and avoid some sterics there. So that would be the product I would get. I would end up getting a cis double bond rather than a trans because of the requirement for the hydrogen to be anti to the bromine during the single step of the mechanism. So this product is thermodynamically favored no matter what, because thermodynamics, I'm only focusing on the structure of the product versus the reactant. And since this product has a more substituted double bond than this one, it's going to be more stable, it's going to be thermodynamically favored. If I use a bulky base, this one's kinetically favored because the transition state is lower in energy when I don't have this big bulky group bumping into the other bulky groups on the other side. When I use a less bulky base, this one is kinetically favored because during the transition state where the pi bond forms, if it's more substituted with carbon atoms, it's going to go through a lower energy transition state than it would if the pi bond formed between carbons where it's more substituted with hydrogens versus carbon. Any questions about any of that? Alright, so that's pretty much it for today. There's a lot of detail there, and that's the basis that we're going to use to continue the discussion on Thursday. So obviously next week you'll be looking at an exam that covers the day 17 and 18 materials, so there's lots of good practice for you to do there related to today, day 17. And then on Thursday we'll get into the day 18 content, which is going to expand on what we talked about. Comparing E1 and E2 mechanisms and looking at different reaction conditions that will promote one mechanism over the other so that you can control the structure of your product. I'm going to end the stream, but if you have any questions, I'll stay on the feed for a little while, so feel free to speak up.